Hi, I am Shanawaz. In this lecture, we will be doing some more examples on metric spaces, and we will introduce the notion of convergence of sequences in a metric space. So, we'll begin with example 3. Let X be a non-empty set and then we define a map D from X cross X to R as D of xy, this is equal to 1 when x is not equal to y and otherwise 0. It may be verified easily that D is a metric on X because one can see that the only output, the only values in the domain of D are 1 and 0. So D of X will be certainly non-negative number, non-negative real number, and by definition it is given to be that D of xy is 0 only when X is equal to y. And symmetry and a triangle inequality also follows from the definition of this metric. So it may be verified easily and that D is a metric on X and this metric is called discrete metric. And the space X with this metric D is called discrete metric space, and the metric space XD is called discrete metric space. Now let us do one more example. Example 4, I think. This is called the L infinity space. The space L infinity consider this L infinity space consists of all bounded sequences of real numbers, bounded infinite sequence I mean. Consider the set X of all bounded infinite sequences of real numbers. I.e. all infinite sequences say x is equal to x1, x2, and so on. This is given to be xi, where I is bigger or equal to 1, such that it is supremum exists finitely, such that supremum of absolute value of xi is finite, where supremum runs over I over the terms of the sequence. Now one can easily verify I think first three metric space actions for this metric which we are going to define. So if x be an infinite bounded sequence, and y equal to yi, where this I is bigger or equal to 1, b 2 bounded infinite sequences. We define a map d from x cross x to r as d of xy. Note that these x and y, they are infinite bounded sequence. We define it to be the supremum of absolute value of the difference of I terms of these two sequences. This supremum runs over I. So one can easily verify the first three metric space actions for this metric D. One can easily verify first three metric space actions for D. Now as far as the triangle inequality is concerned, we proceed as follows. As far as triangle inequality is concerned, let us take another sequence, say z equal to zi, where I is bigger or equal to 1 in this set X. Then we have absolute value of xi minus yi which is same as absolute value of xi minus zi plus zi minus yi, and by triangle inequality this is equal to absolute value of xi minus zi plus absolute value of zi minus yi. Now if we take supremum over I for both these terms, this inequality will remain preserved. So this is if it is less or equal for any I, it will be true for supremum as well. So it is less or equal to supremum xi minus zi, while the supremum runs over I plus supremum of zi minus yi, while the supremum runs over I. Therefore, now this right hand side exceeds left hand side for any I over here. So this will if we take supremum on the left hand side, this inequality will remain still preserved. So we can write it as this is same as d of xz plus d of zy. So therefore d of xy, which is by definition supremum over I xi minus yi, which is less or equal to d of xz plus d of zy. So this d serves as a metric for this space L infinity, which is a space of bounded sequence. So let us make a note here. L infinity is the space of all bounded infinite sequences. So let us do one more example. This is example 5th. This is called the LP space. The space LP. Now these are this is again the set of all sequences which are pair power summable, i.e. Let X be the set of all sequences xi, where this I is bigger or equal to 1, of real numbers such that sigma I runs from 1 to infinity absolute value of xi power p, and taking the pth root. This must be a finite number. So with respect to this, so if we define a metric on D, so if x is equal to xi, where I is bigger or equal to 1 and y is called yi, I bigger or equal 1, belong to x. We introduce the distance function, like we introduce the distance function. Like this, d of x y. So here this d is from x cross x to r. So we define it like this. Sigma I runs from 1 to infinity. Absolute value of difference of term xi and yi, and it is pth power, and then taking pth square root. So evidently d of xy is non-negative, and d of xy is 0 if and only if x and y are equal, and d of xy is same as d of yx. Now as far as the action 4 is concerned, I mean the triangle inequality, that is a direct consequence of Minkowski inequality, which we have learned in the previous chapter. Evidently d of xy is non-negative. So this sum over here, it can't be negative because it is a sum of infinite non-negative numbers, and that cannot be negative. And d of xy, this will be 0 only if and only if x is equal to y, and d of xy is same as d of yx, because taking -1 out of modulus, it won't make any difference. The triangle inequality is the consequence not the consequence, it is actually the Minkowski inequality for infinite sequence. And the triangle equality follows from Minkowski inequality. Let us do another example. This is example 6. This is another metric space, which is a space of bounded functions. The space of bounded functions. Let us consider this set. Let S be a non-empty set. And denote, let us denote, suppose by B of S, B the set of all real or complex valued functions on S, but which are bounded. I.e. If i.e. supremum of absolute value of f of x, it should be finite while this x runs over S. Now if f and g belong to BS, that means they are bounded. Now being bounded, there must exist positive real numbers, say m and n. There exists m positive and n positive, such that supremum of absolute value of fx, where this x runs over S, this is less or equal to m, so m is upper bound for f, and supremum of g of x, where this x runs over S, this is less or equal to n. It follows that supremum of the absolute value of their differences, where this x runs over S, this will be finite. Indeed absolute value of fx minus gx, this is less or equal to absolute value of fx plus g absolute value of g of x, which is again less or equal supremum x in S mod of fx plus supremum x in S mod of g of x. And so this term has at least value 0, so this would be less or equal to supremum x belongs to S absolute value of fx minus gx, which is less or equal to, now this is further less or equal to m, and this is further less or equal to n, so this is less or equal to m plus n. Now let us define a distance function. Define d of f g to be equal to supremum x in S mod of fx minus gx. Note that this expression over here, this is finite quantity. These f and g are just bound functions, they are in B of S. So evidently d of fg is non-negative, and they are and d of fg is 0 if f and g agree on hold the domain set. and similarly d of fg is same as d of gf. So evidently d of f of g is non-negative and it is equal to 0 if f and g agree on the whole set S. Also d of fg is same as d of gf. Now it remains to prove the triangle inequality, and now for triangle inequality we will proceed as follows. It remains to verify the triangle inequality for this function d. Now absolute value of fx minus gx, this is same as absolute value of fx minus hx plus hx minus gx. This is further this is less or equal to absolute value of fx minus hx plus absolute value of hx minus gx. Note that these f, g and h, they are all bounded functions, i.e. they belongs to b of s. So if this is less or equal, if left hand side is less or equal to this expression over here, it will be less or equal to it is supremum as well. So this is less or equal to supremum x in s, absolute value of fx minus hx plus supremum x in s, absolute value of hx minus g of x. So this is equal to d of fg plus d of gh, sorry, d of fh plus d of hg. Therefore d of fg, which is by definition equal to supremum of mod of fx minus gx, where this x runs over s. Now this expression over here, this inequality is true for any value on the left side, so it is true for the supremum as well. So this is less or equal to d of fh plus d of hg. So this d serves as a metric on b of s. This, let us make a note over here. This metric is called the uniform metric, or the supremum metric, or the supremum metric. Let us do some more examples, a couple of examples on metric spaces. So now we'll begin with the example. So now we have example, I think it is example 7th. So this is example 7. Now let us consider a space of continuous functions. The space of continuous functions. And let us consider the set X to be the set of all continuous functions. Continuous functions which are defined say on closed interval, say AB in R. For f and g in X, define the function d as d of f of g. This is equal to supremum over AB, absolute value of f of x minus g of x. Now the measure of distance between the functions f and g is the largest vertical distance between their graphs. For example, if we let us move to the next page. Suppose we have two functions. Suppose the graph of these two functions f and g are like that over here. So let us suppose that this function f is like this. So this is our f here, and let us consider the function g to be whose graph is like, suppose like this. Now the measure of distance between the functions f and g is the largest vertical line, vertical distance between their graphs. So if we look at this point over here, the distance between these two graphs is this. So this is the largest vertical distance. So this quantity over here, this is the this is over d of fg geometrically. So the measure of distance between the functions, between the functions f and g is the largest, is the